Okay, so now we're going to move into some AP style questions, starting with some free response ones. So first we have this situation here, and all three of these questions actually are based on this. But we have two cars here, car 1 and car 2. They're initially moving along a highway, and they're side by side. And they're going to pass car 3 at some instant that is stopped. So all three of them are going to be aligned. And we know some information about the position of these cars for 5 additional time intervals that we can see here on these charts. All right, so we know where they're going. So we're going to use that information to answer a few questions about their motion. So the first question they ask is, during which time interval would car 2 and 3 be moving at the same average speed? So what I'm going to look at is I'm first going to look at car 2 here. And what I see is car 2 actually is moving at a constant speed of about 10 meters per time interval. Okay, we don't necessarily know if it's 10 meters per second, but 10 meters per time interval. So what we want to do is we want to find a situation when car 3 is moves 10 meters in one time interval. So if I look at the distances from 0 to 1, that's definitely less than 10, as is 1 to 2, but 2 to 3 there is right on 10, and if I go from 3 to 4, we've actually exceeded it. You might have noticed that car 3 here is speeding up. So 2 to 3, all right, it moves 10 meters, all right, as does car 2 from 2 to 3. So the answer here is going to be C. So I'm actually going to be thinking about the same equation here that I used in 9, but now I'm thinking about the entire time interval. And so the one that had the greatest average speed is going to be the one that traveled the greatest distance. So I see that car 1 traveled a distance of 40 meters in that time, car 2 traveled 50, and car 3 traveled 50 as well. So 2 and 3 both had the same average speed because both of them traveled 50 meters in that time interval. Moving on to the last question, we're looking at which one had the greatest instantaneous speed at time t5. So what I'm going to do is I'm going to look at their speed during that last time interval from t4 to t5. So I see car 1, not only does it have the lowest average speed, it's actually slowing down. So it's traveling the slowest at the end. It barely moves during that time interval. So it can't be car 1. Car 2 had the highest average speed tied with car 3, but it's moving at a constant rate, 10 meters during that last time interval, and 10 meters during each time interval actually. Car 3, on the other hand, was speeding up. So it had the greatest average speed, and it was traveling faster towards the end because it was speeding up. And we see here that during that last time interval, it covered almost 20 meters. So car 3 is going to have the greatest instantaneous speed at the end of that time interval. All right, moving on to this next one, we have a snail moving along a straight line. So I'm going to set up a straight line here, a number line basically. There's my 0. And I'm told that the initial position of the snail is at -5 meters. So here is our snail. And it's moving away from the origin and slowing down. So it's moving away from the origin, which means its velocity must be going to the left. And since it's slowing down, its acceleration must be going in the opposite direction to oppose the direction of the velocity. So in this coordinate system, we want to know the sign of the position, velocity, and acceleration. So our position initially is -5, so that's obviously a negative. Our velocity is also going to be negative because it's traveling to the left. Our acceleration is going to be positive because it's traveling to the right, or accelerating to the right. So that would be answer choice B here. Negative velocity, negative position, positive acceleration. Okay, and so we have our first AP free response style question here. So we have a situation where there's a plane traveling at an average speed of 500 miles an hour from Philly to LA, flying at 400 miles per hour for the first part over a distance of D1, and during the second part, we're traveling at a speed of 600 miles per hour for a distance of D2. So the first question is a conceptual question, and this is something you will see in a lot of these quantitative, qualitative questions. Okay, in order to average a speed of exactly 500, should D2 be greater than, less than, or equal to D1? And we're going to explain without using equations. So the one thing I would keep in mind, and we talked about this some with the problem in class, in order for the average between 400 miles per hour and 600 miles per hour to be right in the middle, which is this 500 miles per hour, we need to have the plane travel for the same amount of time at those speeds. Okay, so we have to have the same amount of time at 400 miles per hour and at 600 miles per hour. So what does that mean? All right, if we're traveling at the same time for each of those speeds, we're obviously going to go a lot faster or a lot further when we're traveling at 600 miles per hour because we're going faster. So the answer here is going to be that D2 is greater than D1. Now we want to go ahead and explain it. So I would first make the point that in order for the average speed to be 500 miles per hour, you must travel at 400 and 600 for the same amount of time. And then let's link that back to really what the real question is about the distances. So if we're traveling at 600 miles per hour for the same time as 400, we're going to go further while traveling at 600. So that's how we're going to want to make our arguments throughout the year. We're going to state the answer. That's the first thing we're going to do. And then we're going to do our explanation. We're usually going to start with something we know. For example, in order for the average speed to be 500, you must travel at these two speeds for the same amount of time. And then we're going to talk about, a consequence of that point, which is that you have to travel further while going at 600 miles per hour. Therefore, we know this to be true, linking it back to our original statement. Moving on to B here, derive an expression for the time spent during the first part of the trip, which we're calling T1, and the time spent during the second part of the trip, which we're calling T2. So I'm going to start here with my equation for speed, that average speed is distance over time, and I'm going to first think only about that first part of the trip. What things do we know? Okay, well, we know that our distance, we don't have an actual number for it, but we're calling it D1, going all the way back to our initial problem here. We know that our speed for the first part is going to be 400 miles per hour, and our time we just defined to be T1. So setting up that relationship, we can say that 400 equals D1 over T1, and that again is just coming from this equation. And so if we're solving this, we could say 400 T1 equals D1. So if we solve for T1, we end up getting that T1 is going to be equal to D1 over 400. And we're going to do the same thing now for the second part. So the things we know, our distance we're going to call D2, and our time we're going to call T2, and our speed now is 600. So once again, we're using our average speed equation. We're going to have 600 equals D2 over T2. I'm going to go ahead and solve that the same way, and I get that T2 is going to be equal to D2 over 600. So now we've gone ahead and derived an expression in terms of the variables, all right, and numbers given in the problem. So there's part B. For part C, our last part, we now want to solve for D2 in terms of D1, okay? So what I'm going to do is I'm going to start actually, and I'm going to think for a second about what we said all the way back here in part A. And that was that in order for the average speed to be exactly 500 miles per hour, okay, our times must be equal. All right, so I'm going to say that T1 must be equal to T2. This is something that's going to happen frequently, where one part of the problem is then going to go on to help you solve another part. And there is a more complicated way to do this one, and I'll show you in a second. But what I would do is just start with that basic principle. Okay, that's how those times are going to, or those speeds are going to average out to 500. So what we can do then is we can simply say that D1 over 400 is equal to D2 over 600. And we want to solve for D2, so I'm going to cross multiply here, and I get 400 D2 equals 600 D1. And if we go ahead and divide by 400 here, we end up with D2 equals 1.5 D1. And this matches with what we had said before, that D2 is greater than D1. Now, if you did want a slightly harder way of doing this, there is a slightly harder way where you don't use that principle that you know that T1 must be equal to T2. And so what we're going to say for that is we're going to say our average speed for the whole trip is 500 miles per hour. Our time is going to be T1 plus T2, and our distance is going to be D1 plus D2. That means that using our speed equation, we end up with 500 equals D1 plus D2 over T1 plus T2. I'm going to go ahead now and substitute in for T1 and T2. We're left here with this pretty messy double fraction. I'm going to cross multiply. I can then go ahead and simplify some of these fractions. And so what I end up getting is 5/4 d1 plus 5/6 d2 equals d1 plus d2. I'm going to move this d1 over to this side and this d2 over to that side to separate out the two variables. So when I do that, I end up with 1/4 d1 on the one side, because the 5/4 minus the 1 d1, and I end up with 1/6 d2 on the other side, because I had 1 d2 minus 5/6. In order to solve this, I'm going to multiply both sides by 6 to get d2 all by itself. What I end up with is 6/4 d1 equals d2, which would be the same as 1.5 d1 equals d2. So this is a slightly messier way of doing it. Definitely a little bit more math involved, but perfectly valid as well.